Mr. Gibson here. Today we're going to finish up this introduction unit on the physics toolbox, and we're going to focus in on these concept of precision versus accuracy. So far we've reviewed the SI measurement system, that there are 7 fundamental measures that we can derive all other measurements in physics from. And then we've also learned how to use dimensional analysis to evaluate answers and convert from one unit of measure to another. What we're going to focus on now is what's the difference between precision and accuracy, and also look at how do we determine the precision for a given measurement method and accuracy for a given set of measurements. So let's jump right in and start by defining precision. Precision refers to the reproducibility of the measurement and the degree of exactness of a measurement. So really there's 2 different ways in which we can think about this concept of precision. Okay, so let's kind of talk about them separately. The first is the reproducibility. Okay, so if we're making a measurement, we make the same measurement on the same object with the same equipment, do we get very similar results each time? Do we get values that are very close to each other? So if we get them very close to each other or exactly the same each time, we would say that is a very reproducible measurement and has high precision. The second way we can think about it is the degree of exactness, okay? And this one definitely depends on the instrument itself. Let's look at an example of that. Okay, the instrument itself, the technique used, and it really depends on how fine the division on the scale of the instrument is. So the greater or smaller the divisions on the scale of the instrument, the more precise. And the rule of thumb is that the precision will measure as 1/2 the smallest division that the instrument uses. Now let's look at an example and this will make more sense here. Here's something we're all familiar with, right? This is a ruler and it shows a centimeter scale. Okay, so each of the numbers, 1, 2, 3, represents a centimeter. But the smallest division you can see are the lines in between the centimeters. So if we were to count those carefully, we'd see there are 9 lines or 10 spaces, right? So each space represents 1 millimeter. Okay, so we would say that 1 millimeter is the finest division on the scale of this instrument, right? It's a ruler used for measuring length. So if we said, what is the precision that we can measure to using this ruler? It's 1/2 of what that smallest division is. So in other words, 1/2 of 1 millimeter would be simply 1/2 millimeter, right? 0.5 millimeters. So if I ask you to make a measurement using this, you could tell me it's 31 millimeters or 46 millimeters. Or you could say 35.5 millimeters, right? If you believe the length of the object falls somewhere in between the smallest divisions, the best you could say is it's 1/2 of that, right? We won't kid ourselves to think that we could say, oh, it looks like it's 0.2237 of a millimeter between those 2 lines, okay? So 1/2 of whatever the smallest division is how we will define its precision. So let's look at some more examples here, okay? Oh wait, this one we just did, right? Sorry about that. This is a same example here of a millimeter being the smallest division, therefore 1/2 a millimeter would be our precision. So let's move on and look at the next one here. Here's a graduated cylinder. So You've used these in chemistry, right, to measure volume in milliliters. Notice we have the units up here. So if we look at a close-up view of this, we have 40 and 50 milliliters, and then we have further divisions between those. So the question is, how much does one division represent in terms of milliliters? Well, we're taking 40 to 50 and dividing it into 10 spaces. So one division would give us 1 milliliter. So the precision would simply, again, be half of that. So 1/2 a millimeter or 0.5 milliliters. That's the greatest precision to which we could make a measurement using this graduated cylinder. Let's look at one more here of a graduated cylinder. Okay, now these are in units of milliliters. Okay, the question is, how much does this one division represent? Well, the labeled levels are 50 and 100, and we have 1, 2, 3, 4, 5 divisions for that. So each small division would be 10 milliliters. So the precision would be half of that, 5 milliliters. All right. Okay, here's one more. I'm not going to say anything here for a few seconds. Pause the video. See if you can determine what the precision of this would be. Now, here's a beaker, right? Beakers aren't as precise, clearly, as a graduated cylinder. Okay, so it tells us, right, that the units are milliliters. And so now the question is, how many milliliters are there between the lines? Well, in this case, each line is labeled, so it's fairly easy, right? We would go from 200 to 250, so that means the smallest division is 50 milliliters. So the precision that we could measure to using this common beaker is 25 milliliters, right? Much less than what we can do with a graduated cylinder. So if you want to measure volume to a high degree of precision, we would use a graduated cylinder. Excuse me. All right, let's talk about accuracy now. This has to do with how well the measurement agrees with the real value or accepted standard. So what do we mean by that? Well, let's think about how we normally make a measurement, and think of this, maybe you're making a measurement of mass on a scale. And so often to check the accuracy or to make sure we're making an accurate measurement, we use what we call a 2-point calibration. So the first point is, does it read 0, right? So you often do this when you're measuring mass on a scale. Before you put the object on there, there's actually a button that allows you to zero out that scale, okay? So that's this first calibration point that we're doing. And then the second is if we had a standard that we knew exactly its mass, we could put that on the scale and see how closely it reads to the correct value of that standard. Okay, now often we don't do this in the lab, but if we do periodically have our scales calibrated, and this is exactly what they do. They put a known standard on there and adjust the scale internally to make sure it agrees with that known standard. So here's examples, right? Electronic scale, and then this is what the standards might look like. Each one is precisely manufactured and calibrated to a certain mass. It's usually inscribed on the standard, and then we can use that to measure how accurate our scale is. Okay, let's look at some examples here that we can better understand conceptually the difference between precision versus accuracy. So we have 4 targets here. Each target, we have 5 locations, right, where we've thrown the dart and where they've landed. And we want to look at each one and see how would we describe qualitatively that process's accuracy and precision. Okay, so we're either going to say it has high or low accuracy or precision. So let's start down here in the bottom left-hand corner, where we see we've got 5 points that are all widely scattered. would we say that it has very good precision? Now remember, precision is the degree to which we can repeat the process so that the outcome is very much the same each time, or we make a measurement and we get very close to the same measurement each time. So I think we can say here with these points scattered, right, that it has low precision because we're not very consistent in terms of where we hit the target. The accuracy also we would say is very low. If you kind of say, well, where would the average be of these 5 points? It would certainly not be near the bullseye. Okay, so we're going to say it has low accuracy and low precision. Now let's move to the one up above here in the top left-hand corner. We see 5 points that are, let me put my little pointer on here, 5 points that are very close together, but still not centered on the bullseye, right? So in this case, we would say it has low accuracy, but high precision. We have a very consistent process in terms of trying to hit the target. We're just not hitting it in the center. Let's move now to the bottom right here. We have points that are fairly close together, not as tight as some of the others. But if you look at the average of where those points hit, they are very close to the bullseye, the center. So here we might describe high accuracy, but precision not as good, not as tightly grouped together as some other examples. Let's go to the top right here. We see our 5 points are all almost right in the bullseye and very close together. So this would be an example of both high accuracy and high precision. Okay. All right, let's go to the last concept here, and that is how do we actually quantify or measure the accuracy of a measurement or a set of measurements. And the way we do that is by calculating the percent error. Okay, so percent error formula is given here. Make sure you get this in your notes. It's the measured value minus the actual value, and then divide that by the actual value. Now we want to have our error in percentage, so we're going to multiply by 100. That will give us percentage in our final answer. So let's look at an example of that. Let's say we want to find the percent measurement error, and the actual value is 50 grams. Let me get my pen going here. So the actual value is 50 grams. And the 3 measurements we made are given here. So we make the same measurement 3 different times, and these are the values that we get. Now, to say how accurate that measurement is, the first thing to do, and you know we often do this in the science labs, is to take the average of those 3 measurements. Okay, so let's go ahead and do that. Let me clear this. So that we take the average by simply adding up our 3 measurements and dividing by 3, since we made 3 measurements, okay? And that gives us an average of 48.7 grams. That's the value we're going to use as our measured value, or average measured value, and use our percent error formula. So let's plug that in. 48.7 minus 50, remember 50 is our actual value, and then divided by that 50. Multiply by 100, and we get a percent error of negative 2.6%. Now, why the negative? Well, it's negative because our average measured value was below or less the actual value. So the negative just kind of tells us which side of the actual value we're on. If it came out to be positive, we'd have a value that's above the actual value or greater than. Okay. Now, if we were doing a lab in physics, if we get something that's accurate to a known or standard value of 2.6%, that's pretty good accuracy for a high school physics lab. If you get something that is 30 or 40% off, then you would say, whoa, we did not make some very accurate measurements here. We might even need to go back and check our measurements or redo some. All right. So this is how we measure percent error. or the accuracy of a process is by calculating the percent error. So let's clear this. So that's the lesson for today. The last piece again in this physics toolbox that we're talking about. Can go back up here to our original objectives. So we now know how to describe the difference between precision and accuracy, and we can determine the precision for a given measurement method by calculating the percent error. Right, there's a assignment that goes along with this video. It's a Google form or quiz you can complete as homework, and the rest of the details are there in your Google Classroom.